A perfectly spherical soccer ball is being pumped to have the regulation circumference of 69 centimeters. Air is being put into it constantly at a rate of 20 centimeters cubed per second. Find the rate at which the radius of the soccer ball is increasing when the circumference of the soccer ball is 1/2 of regulation size. So, I have 3 methods to solve this. This is method 1. And it's using formulas. Alright, so we need to figure out what we're trying to find. So we're trying to find the rate at which the radius of the soccer ball is increasing. Well, radius is r, right? And the rate at which it's increasing is going to be that. The change in radius over time, right? So which is going to be dr dt, because we're trying to find like what the rate is at this certain size. So dr dt is what we're trying to find, and we can figure out the radius because we know the circumference is half of regulation size. So regulation size is 69 centimeters, right? And the formula for circumference is c equals 2 pi r, right? So it's half of regulation size, so the circumference is 69 over 2 equals 2 pi r, right? And you divide 2 pi from both sides, and then you get 17.25 over pi equals the radius. So we know the radius is 17.25 over pi. So now we need to, it says the radius of the soccer ball is increasing, and we know air is being put into it constantly at a rate of 20 centimeters cubed per second, and 20 centimeters cubed is a measurement of volume, right? So what we need to do is we need to figure out what this is. So this is the rate at which this is it's being put in. So that's going to be the dV dt, or the volume over time, because it's 20 centimeters cubed per second. So we know dV dt is 20 centimeters cubed per second. And also this is centimeters, I forgot to label it. And we don't know volume. So what we're trying to find here, this is what we know. So we have to try to find an equation that relates these so that we can find dr dt. So we can use the formula for the volume of a sphere, because as was stated in the problem, it's a perfectly spherical soccer ball. So the equation is V equals 4/3 pi r cubed. So we don't know volume, but we do know the radius, and we don't know dr dt. So in order to get the values that we know and the value that we don't know, we have to differentiate the whole equation with respect to t. So you do d dt of both sides, and that's going to give you dv dt equals, okay, so to differentiate that, we can just use power rule, which is a way of differentiating that doesn't use the whole formula with the limits. So you multiply 3, so that's going to give you 4 pi r squared dr dt, because it's like multiplying by d dt. We're giving you dr dt times 4 pi r squared, which is also the formula for the surface area of a sphere. So now we have the equation dv dt equals 4 pi r squared dr dt. We know dv dt is 20 centimeters cubed per second, which we plug in. And we know r is 17.25 over pi centimeters, so we plug that in as well, 4 pi 17.25 over pi squared er dt. And now we can simplify the whole equation by dividing this by 4 pi 17.25 over pi squared. And that's going to give us the r dt equals 0.05279 centimeters per second, because we have to, we have to use units. So this is the rate at which the radius is increasing when the circumference of the balloon is, the soccer ball is half of regulation size. And I rounded to 5 sig figs. Okay. So that's method 1 and method 2. Approximating the slope of a line. Alright, so we know that we're trying to find the rate when the circumference equals 69 over 2. But we're trying to find the rate of the radius. So the circumference really has no use to us. So we're going to convert that to the radius, which we already did in the previous problem, giving us 17.25 over pi as the radius. So rate that the radius is changing when it equals 17.25. So what I wanted to do was I wanted to find the volume when r equals 17.25 over pi. So I did that for thirds pi 17.25 over pi cubed. Okay, so when I simplified this, I got v equals 693.43585. So at the time that we're trying to find the rate of, the volume equals this and the radius equals this. So as you know, to approximate the slope of a line at this point, let's say this is 2, basically you could find one point ahead of it and one point behind it, find the y value of that point, find the x value of this point, draw a line through it, and the slope of that secant line should be about equal to the tangent line at this point. So this is going to give us an approximate answer, not the exact answer, unlike the other method of using formulas in calculus. Alright, so I have to find one less and one above. So I know it changes 20 centimeters cubed per second. So we have the volume 1 second before and 1 second after, as we did in this case here. So right now we have this and we're trying to find this and this, right? So we have to subtract 20 to get 673.43585 and 713.43585. And so that's basically 1 second after and 1 second before, because it's 20 centimeters cubed per second. So what we have to do now is we have to find the radius corresponding to these volumes. So you can do that by plugging into the formula v equals 4/3 pi r cubed, right? So we have the formula and we plug in these values. 673.43585 equals 4/3 pi r cubed. And when you do that, you get, let me calculate. So 673.43585 times 3/4 divided by pi, and then you have to find the cube root of that. And so that's going to give me r equals 5.5 43754, because I went to 5 decimal places. So if I do that same thing for 713.43585 equals 4/3 pi r cubed, you get radius. And keep in mind that we changed to radius because we're trying to find the rate at which the radius changes, and the volume has no use to us. The only reason we use the volume is because we know the rate the volume is changing every second, but we don't know the rate at which the radius is changing every second. Okay, so we have to do the same thing as we did before. 713.43585 times 3/4 divided by pi, and find the cube root of that. And that's going to give us 5.54313, rounded to the 5th decimal place. So now we know the 3 and 1 from this equation, so this and this. So in order to find slope, we need, the 3 and 1 is the second, so we know the y's. So in order to find slope, it's change in y over change in x, or y2 minus y1 over x2 minus x1. So we know the y's, so let's put that into our equation. 5.54313 minus 5.43754, right? And you divide that by, so it's gonna be, let's say what the radius that we're trying to find, okay, sorry, let's just say this, it's at 2 seconds. It really doesn't matter because the difference is going to be the same no matter what position it is. It's just a horizontal translation. So let's just say it's 3 and 1, right? This is y2, y1, x1, x2. So we solve this, and then we get 5.54313 minus 5.43754 equals that, over 3 minus 1, which is just 2, and you get dr dt, the rate at which the soccer ball's radius changes over time, equals 0.05280. So if we compare it to what we got in the previous one, centimeters per second. If we compare it, it's almost exactly the same, because the difference is only 1 second, and it takes a lot longer than 1 second or 2 seconds to inflate the soccer ball. So when we have to graph, instead of doing it at a difference like this, we're only doing it at a difference like this because this thing is a lot longer. Okay, so method 3. Alright, so method 3 uses more of the calculator. So use calculator to find best fit line, and use dy dx function on the calculator. Okay, so in order to get the best fit line, I decided to use 4 different values. Like I did in the previous method, I found the radii of the volumes, and then I found the best fit line in between them. So what I did was, in order to get the best fit line, you have to use many different values that are far apart from each other. So I chose volumes of 200, 300, 400, and 500. So basically this is like what I did before, except instead of approximating the slope between the 2 points, I actually find the line so that I could have the equation, and then I use the calculator to differentiate that equation and then find the slope at that point. So I need to have the equation first. So in order to get the equation, I use these. So I have to find the radii at these points. So, and if I do all these right now, it's going to be kind of tedious, so I'll just list them out. So it's going to be, for this one, it's going to be 3.62783. For this one, it's going to be 4.15283. For this one, it's gonna be 4.57078, and finally for this one it's going to be 4.92373. So now that we have that, we need to relate the radius to time, because we're seeing how the radius changes over time. So how do we relate this over time? Well, we know the volume changes at a fixed amount. So let's just say that at 0 seconds, the volume equals 0, right? So, well, if that's true, and centimeters cubed per second, sorry, and if that's true, and it inflates 20 centimeters cubed per second, then after 10 seconds, so times 10 to get, and then you'll get 200 centimeters cubed after 10 seconds. So that means that you can, because 10 seconds correlates to 200 centimeters cubed, it also correlates to the radius of 3.62783. And you could do the same thing for each of these. See how many times you have to multiply 20 centimeters cubed by like what number to see what time correlates to the radius. And it doesn't really matter what you start out with. Like, you could start out with a volume of 100. It's just a matter of horizontal translation again. So we get the points. We want to put time on the x-axis and radius on the y-axis, as we did in all our other problems. That's going to give us 10, 3.62783, and 15, 4.15283, and so on. So what we want to do is we want to use the calculator to find the best fit line. So I'm going to do that right here. So I'm going to edit the plot, and I'm going to plug in the numbers. So if the x values are going to be 10, 15, 20, and 25. So I plug those in. 10, 15, 20, and 25. The y values that correspond to those are going to be 3.62783, 4.15283, 4.57078, and 4.92373. So now that we know those, we go to Stat, Calc, and if we solve the volume equation in terms of R, so it gives us R equals something. Because the volume equation is 4/3 pi R cubed, if you solve for R, it's going to give you 3/4 pi V, and then you're going to get the cube root of that. But the cube root is also equal to V to the 1/3 power times like some number, because we know this is going to be some number. So this is going to be a power function. So we could use power regression here. We could use x list as L1, y list as L2, store the regular equation in RY1 so that we could graph it later on, and we calculate that. It's going to give us this. And as you see, the B is correct because it approximately equals 1/3, right? Because 1/3 is 0.3333 repeating. So now that we have that plugged into here, we want to find the rate at which the radius is changing when y is also the radius. So when the radius equals 17.25 over pi, right? So we have to make a line at 17.25 over pi and find the intersection between this line and this line, because the intersection is when y here equals 17.25 over pi, and that's going to give us the x, and then we could find dy dx at that point. So first we want to set up the window. What I did was I set the window from 0 to 50 because I saw that it was 10, 15, 20, 25, and I remember that it was about like 693 point something. So 600, so that's 700, and 700 divided by 20 is no more than 50. And the y min and the y max I set 4 to 6 because, as you can see, like these values, it's probably not going to go over 6 by the time it reaches 693. And I set the scales too accordingly so that it'll fit. So when I graph it, I just have to wait for it to graph. It's going to graph the function, and then it graphs a line. So what I have to do is I have to find the intersect between them using the intersect function. This is the first curve, this is the second curve, even though it's not a curve. And guess, oh, I guess it's somewhere around here. So the intersection is going to give me as y equals 5.49084555, which is 17.25 over pi, and this x value. And the x value is arbitrary. So I use second calc again, and you see there's a dy dx function, and basically the dy dx, you can replace y for r and x for t, giving us dr dt, which is exactly what we're trying to find. So if we find dr dt at this point, it's going to give us dr dt equals 0.05289. So this is what we get for the third method. And if you compare what you got from the other methods, sorry, let me find what I got. Okay, so this is what I got on the method where I used the formulas, 0.05279. So this is the exact answer. This is what I got when I approximated this using only 2 points, and I got 0.05280, which is close but not exactly the right answer. And then for this one, where I use completely random points throughout the line rather than using just the points that are close to it, I got 0.05289, which makes sense because, you know, it doesn't give me the exact equation when doing a regression. So this is the furthest away, this is the second closest, and this is the exact answer. And we're done.